150 million ornaments are used every year in the United States alone. This staggering number is more than the country's entire population. Yet few people realize that most of them originate from specific small villages located in Germany, Poland, and Mexico. But this is just the beginning. Why do these artisan workshops remain the beating heart of Christmas around the world? It seems that modern mass production would have fully taken over long ago, but the answer lies in a centuries-long craft tradition that machinery cannot replicate. Skilled workers transform raw glass through shaping, coloring, and silvering. One can notice how the process breathes life into pieces that become icons of the holiday season. The molten material gradually hardens into a form capable of holding vibrant color and reflection. At first glance, the result is a simple, fragile sphere, but in reality, it drives a multi-billion-dollar industry. From forest-side villages in Europe to factories running day and night, the ornament world holds on to one unchanging value. It turns something fragile into an object that preserves light, memory, and emotion. Thus, the tiny object secures its special place in global Christmas culture. 500 years have passed since red apples were hung on evergreen trees to symbolize light in the middle of winter. German artisans evolved this tradition by blowing glass into hollow spheres. The custom spread across Europe and reached the United States, creating an industry worth billions of dollars. But this is just the beginning. Why did the material choice shift so drastically? The transition involved more than just aesthetics. At first glance, fruit was sufficient, but in reality, glass reflected light more brilliantly than any material of that time. Today, ornaments live in two very different worlds. One can notice how artisan workshops spend up to 10 days on a single piece. The process moves layer by layer, from color to brushwork and the silver coating inside. It gets more complex further on. Automated factories turn out 60,000 pieces per hour to meet global demand. Both rhythms sustain a Christmas symbol that has endured for more than half a millennium. The finished ornaments are ready for use. Half a millennium of tradition supports the craft. Yet silica sand remains the primary ingredient used to make glass. Before it reaches the furnace, however, the raw material must be refined to achieve the required level of purity. Inside the plant, the sand passes through multiple screening stages to remove soil, gravel, and particles of inconsistent size. But this is just the beginning. A high-pressure washing system takes over the cleaning process. Why is such intensive washing required for raw sand? The grains might appear ready for use after the initial screening. This system strips away organic matter and fine dust clinging to each grain, bringing the material to a dry, clean, uniform state. On some production lines, the sand also goes through magnetic separation to remove trace amounts of iron oxide. At first glance, this impurity seems minor, but in reality, it is a factor that can give finished glass an unwanted green tint. Once the refinement stage is complete, the sand is dried. It gets more complex further on. Engineers blend the silica with soda ash and limestone in precise proportions. The consistency of this mixture determines the quality of the future melt. It ensures the glass will melt evenly, reduce fewer air bubbles, and achieve the level of clarity required for thin ornament glass. Once the refined silica sand is blended with soda ash and limestone, the batch is fed into a continuously operating furnace. Inside the chamber, heat can exceed 2,000 degrees Fahrenheit. This is equal to about 1,093 degrees Celsius, enough to break down the structure of the silica grains. One can notice how the intense heat gradually transforms the entire batch into a liquid state. However, the material does not become transparent right away. One can observe the material beginning as a thick, cloudy mass that slowly turns into molten glass with high viscosity. Inside the furnace, heat flows are carefully controlled so the batch warms evenly, preventing cold spots. a factor that can create air bubbles or streaks in the final product. The process is only gaining momentum. At the end of the melting zone, a refining section plays a crucial role. Here, any remaining impurities and trapped air bubbles are removed. It is visible how the glass reaches the crystal purity needed for ornament blowing. When melting is complete, the molten glass becomes a uniform, bright, and stable stream of material. The substance is ready to be drawn into thin glass tubes, the base stock from which every hand-blown or machine-blown Christmas ornament begins. A few tenths of a millimeter, exactly the wall thickness required for a high-quality glass ornament to survive the decoration process. In artisan workshops, the production cycle begins after the molten glass leaves the furnace. Instead of being blown immediately into a sphere, the raw material must first be drawn into a perfectly uniform tube. This intermediate form is ideal for ornaments because the thin wall allows the glass to expand evenly in all directions during the later stages, reducing the risk of uncontrolled thick or thin spots. One can notice how the artisan approaches the molten mass with a heat-resistant metal rod, rotating it steadily to keep the temperature evenly distributed. Why is this intermediate tubular stage so critical for the final product? At first glance, it seems like an unnecessary complication to the workflow. However, without a preformed tube, the glass would possess structural irregularities that make the final sphere fragile and uneven. The artisan gradually pulls back to stretch the material into a long, slender tube while the glass is still viscous. The tube's thickness depends directly on the pulling rhythm and the speed of the hand's rotation. A slight change in velocity can noticeably affect the tube's weight and future heat response. Once the tube reaches the desired length, it is moved away from the high heat zone. But this is just the beginning. The tube is allowed to cool slowly in open air while rotating on a heat-resistant rack. This continuous rotation maintains roundness and reduces internal stress, which is often a cause of cracking. Any section showing uneven thickness or slight warping is rejected immediately, since even a small weak point can cause an ornament to break. Tubes that meet the standard are cut into uniform segments. When the glass preform is still glowing hot, the artisan brings it into direct contact with trays of fine-colored glass particles, known as frit. It looks outwardly simple to coat the glass in dust, but in reality, this process determines the longevity of the color. Under intense heat, these particles instantly adhere to the surface. Instead of sitting as a temporary coating, the frit softens and bonds with the outer layer of the glass. This allows the color to become part of the material structure, giving the surface depth. The preform is then returned to the heat for a refusing stage. It gets more complex further on. The goal is to soften the frit just enough for it to fuse into the surface. One can notice how the colored particles begin to spread and blend, creating visual depth rather than a flat layer. Continuous rotation eliminates the boundary between the colored layer and the glass core beneath. Once the color has stabilized, the preform is gently cooled to lock in the surface structure. If the temperature is not precisely controlled, the color can burn or turn cloudy. Therefore, the heating system must regulate heat very carefully to preserve the original tone. This is the moment when effects such as marbling or metallic shimmer are effectively frozen into the material. When the color layer has stabilized, the blowing process begins. The artisan returns the preform to the heat to soften the tube walls evenly, then introduces air into the hollow interior with adjusted pressure. Under the combined effects of airflow and surface tension, the glass expands from within. It is visible how the material naturally balances itself into a spherical shape. Throughout the blowing process, the preform is rotated steadily to distribute material evenly. Rotation controls wall thickness, which is often measured in mere fractions of a millimeter. The final shape depends primarily on the rhythm of the breath, and the motion of the hands. Stopping at the right moment is critical. Blowing too far leaves the walls thin and fragile, while stopping too early produces a heavier sphere. Once the desired size is reached, the ornament is separated from the tube, leaving a small neck in place. Once the hanging stem is securely attached to the top of the sphere, the glass forming process is complete. The glass still retains residual heat, but no further manipulation is applied to avoid deforming the body. Thus, the shape of the ornament transitions to the next production phase. (1,100 degrees Celsius is the temperature required to begin the transformation of raw materials into the first industrial forms. This marks a definitive shift from manual craftsmanship to a high-speed production environment capable of meeting global demand. To satisfy the requirement for millions of glass ornaments, the industry relies on a dedicated tube drawing process designed for consistency. Inside the plant, molten glass flows continuously through a precise tube-forming die that sets the initial diameter of the cylinder. A controlled pulling system draws the material forward at a strictly regulated speed, ensuring that the wall thickness remains perfectly uniform along the entire length of the line. The process is only gaining momentum. One can notice how the glass tube passes through a cooling zone where the red glow fades as the internal structure stabilizes. Automated cutters then slice the continuous line into standard lengths suitable for further processing. These blanks achieve a high level of dimensional consistency, making them the ideal foundation for industrial-scale ornament production. The cut sections are immediately transferred to a heating area where they are prepared for the forming stage. Each glass cylinder is held within the stable flame of an industrial torch, rotating continuously to allow the heat to spread evenly around the entire circumference. Why is the heating time for each tube section never fixed? The flame burns with constant intensity to soften the walls. This is necessary because the duration varies depending on the specific wall thickness, glass composition, and the amount of residual heat already stored in the material. Engineers monitor the condition of the glass directly by observing subtle changes in color and the material's response to rotation. Once the walls reach the ideal plastic range, the tube is withdrawn from the flame. At this point, thermal uniformity determines the future roundness and strength of the sphere. As soon as the glass reaches a stable plastic state, the blowing process begins without a single second of delay. Compressed air is introduced into the heated end with precisely controlled pressure, forcing the walls to expand from within. It is visible how the tubular form gradually swells into a perfect sphere under the force of the airflow. Throughout this expansion, the tube rotates ceaselessly to distribute the material, preventing thin spots. While standard ornaments rely on pressure and rotation, specialty designs like pine cones or teardrops pass briefly through shaping molds. These molds do not clamp the glass but act as guides, limiting the outline while maintaining the clarity of the walls. Once the geometry is defined, blowing stops immediately, and the shape is locked in forever. But this is just the beginning. Following the forming process, the hollow spheres move to the silvering stage to acquire their characteristic reflective shine. A measured amount of silvering solution is injected through the stem into the interior of the hollow globe. The ornament is rotated evenly, allowing the liquid to coat the entire inner surface without pooling. A chemical reaction is triggered instantly, causing metallic silver to precipitate and bond directly to the glass structure. One can notice the surface transitioning from transparent to a mirror-like silver finish within moments. This internal layer becomes the reflective base for all subsequent colors. Excess solution is drained and the ornament is rinsed to remove reaction residue. Once the silver layer stabilizes, the spheres are mounted on conveyor fixtures for the exterior finishing stage. Here, Base coat paint is applied as the ornaments rotate slowly, settling into a thin, uniform layer that protects the silver inside. It gets more complex further on. Depending on the product line, decorative elements are added, ranging from hand painting to glitter and decals. Every detail must bond securely to the base coat to maintain sharp definition as light reflects off the silver layer beneath. Once the decoration is complete, the ornament reaches its final appearance, defined by a balance of color and light interaction. From here, the focus shifts to the creation of heavy-duty glass containers. Engineers use specialized CAD software to design molds with high precision, ensuring every dimension meets specifications before the digital file becomes a heat-resistant metal mold. These molds are installed into the double-blow production line, the standard for shaping hollow items like bottles and jars. The process initiates by releasing drops of molten glass, known as gobs, cut from a continuous stream at temperatures reaching 1,100 degrees Celsius. Gravity pulls the gob into the preliminary mold, where a jet of compressed air forces the material outward against the walls. This creates a parison, a hollow bubble with a narrow neck, which is then transferred to the final mold. Here, a second burst of air stretches the soft glass until it hugs every detail of the metal cavity. In mere seconds, the full shape of the bottle is born. At first glance, the movement of the machine seems simple and repetitive, but in reality, every valve and sensor is synchronized down to 1,000th of a second to produce hundreds of thousands of flawless bottles daily. It is visible how the fresh bottles glow red hot in the dark workshop as they leave the mold. Robotic arms glide into position with programmed grace, picking up each bottle and placing it onto the moving conveyor. There is no rush and no noise, only flawless coordination. The belt moves the bottles toward the cooling tunnel, where the temperature drops gradually over tens of minutes. This slow process prevents the glass from cracking due to thermal shock. And this is not the limit. An inspection zone awaits the cooled bottles, where optical sensors and high-speed cameras scan for cracks, bubbles, or scratches. Advanced systems rotate each bottle to check the mouth for chipped rims or size errors. Any flaw results in immediate removal from the line. The flawless bottles continue to the palletizing area, where automated robots arrange thousands of units into layers. Protective sheets are placed between layers, and the entire stack is wrapped in film for transport. But before new glass can be made, old glass must be reclaimed. To recycle glass, the system relies on a steady supply of used material. In many European nations, reverse vending machines installed on city streets allow consumers to return bottles for a small refund of 10 to 20 cents. This system ensures that tens of thousands of bottles are pre-sorted and clean before they even reach the factory. When the machines are full, specialized trucks collect the material in large plastic bins. 150 tons, or roughly that equivalent in volume, can be processed by the recycling chain daily. But it starts with a single truck carrying 20,000 to 30,000 bottles. The drivers back up to massive storage bays and release the load, sending a cascade of bottles tumbling down. In minutes, the ground fills with mountains of glass in greens, browns, and clears. These piles are the starting point of the recycling chain. Transition to the next level. Massive loaders scoop up the waste glass and dump it into the plant's feed hopper with a thunderous crash. A steel conveyor carries the stream, mixed with dirt and sand, into the facility. Vibrating screens shake the material violently to separate dust and grit. Workers stand along the line to manually pull out paper and plastics that machines might miss. One can notice how magnetic separators pull metal bottle caps out of the stream, while the glass continues forward. The material is now roughly 80% clean. The glass then enters a hammer mill, where high-speed rotating hammers smash the pieces into tiny fragments called cullet. Any piece too large is sent back for recrushing until uniformity is achieved. Everything only gets more complicated. Air suction systems blast the cullet to strip away leftover labels. The final cleaning step involves an optical sorting system where laser sensors scan each fragment for color and composition. If a stray color or ceramic shard is detected, a precise puff of air shoots it into a separate stream. This happens at a speed of tens of thousands of pieces per minute, ensuring perfect color purity. Sorted cullet is piled into stockpiles, ready for melting. To create new glass, the cullet is mixed with silica sand, soda ash, and limestone. The addition of 20 to 70% cullet allows the mixture to melt at lower temperatures, reducing energy consumption by up to 40%. The mixture is heated in a furnace until it becomes a homogeneous liquid. For automotive glass, the molten material flows onto a bath of molten tin in the float glass process. The glass floats on the tin, spreading naturally into a continuous ribbon with a perfectly flat surface. The temperature here is held between 1,800 and 2,000 degrees Fahrenheit. Edge-forming rollers control the width and thickness as the ribbon moves forward. It seems obvious that the glass is flat, but in reality, furnace operators must continuously monitor the ribbon for microscopic distortions that could warp a driver's view. The ribbon leaves the tin bath and enters an annealing layer where the temperature drops from 1,200 degrees Fahrenheit in controlled increments. This removes internal stress, ensuring the glass will not shatter during mechanical handling. Once cooled, the ribbon moves to the cutting section. Diamond blades score the surface, and a braking system snaps the sheet cleanly along the line. The process does not end at this stage. After quality inspection, the flat sheets are sent for edge processing, where grinding wheels remove sharp burrs. High-pressure washing systems clean the surface before the glass enters the bending chamber. Each vehicle model requires a specific curvature, so the glass is placed on a mold and heated to roughly 1,150 degrees Fahrenheit. Gravity or press molds shape the softened sheet into the precise contour of a windshield. Lamination follows the bending process. A transparent PVB film is placed between two curved sheets, and the stack is pressed by heated rollers. An autoclave treats the unit under high pressure, bonding the layers completely to create a shatter-resistant structure. Finally, a polymer gasket is pressed around the perimeter to seal the glass. The finished automotive glass is inspected one last time by optical sensors before being placed onto padded steel racks. The material is now ready to leave the factory and move to the assembly line for installation.